Today we're going to do section 5.3, diagonalization. The goal here is to develop a useful factorization, A equals P d P inverse, when A is n by n. We can use this to compute A to the k quickly for large K. The matrix D is a diagonal matrix, i.e. entries off the main diagonal are all zeros, and dk is trivial to compute, as the following example illustrates. So example 1, let D be 5, 0, 0, 4. Compute D squared and D cubed. In general, what is D to the K, where K is a positive integer? So let's first do D squared. D squared would be both of these multiplied together. And I would end up getting 5 squared, 0, 0, 4 squared. And then let's go ahead and look at D cubed. So we would multiply the same matrix by itself 3 times, which would be the same as taking our previous answer for D squared, multiplying it by this, and you would end up getting 5 cubed So in general, d to the k for this one would be 5 to the k, 0, 0, 4 to the k, for k greater than or equal to 1. Let's look at example 2. Let A be 6, negative 1, 2, 3. Find a formula for a to the k, given that A equals P d P inverse, where P is 1, 1, 1, 2, and D is 5, 0, 0, 4. And P inverse is 2, negative 1, negative 1, 1. So let's first look at A squared. And A squared equals A times A, which, since A is P d P inverse, this would be P d P inverse times P d P inverse. And then I could rewrite this as P d P inverse times P d P inverse. And if you notice, P inverse times P, that's the identity matrix. So this would then be P d D P inverse, which is the same thing as P d squared P inverse. And since we know that D squared would be 5 squared, 0, 0, 4 squared, we could write this as 1, 1, 1, 2 times 5 squared, 0, 0, 4 squared times P inverse, which was 2, negative 1, negative 1, 1. So then let's go ahead and look at this for A cubed. And A cubed would be the same as A times A squared. And if you look at this, that would be A is P d times P inverse. A squared is P d squared P inverse. And this would be P d P inverse times P d squared P inverse. And remember that P inverse times P is the identity matrix. So then this would be P d times D squared P inverse, which would then be P D cubed P inverse. And we would have 1, 1, 1, 2. We know based on example 1 that this would be 5 cubed, 0, 0, 4 cubed times 2, -1, -1, 1. So in general, for k greater than or equal to 1, a to the k would equal pd to the k p inverse. So using this, we would have 1, 1, 1, 2, 5 to the k, 0, 0, 4 to the k, times 2, -1, -1, 1. Then multiplying these, we would get 5 to the k, 4 to the k, 5 to the k, 2 times 4 to the k, I believe, times 2, -1, -1, 1. And then multiplying again, our final answer for our formula would be 2 times 5 to the k plus -1 times 5 to the k. And then 2 times 5 to the k plus -1 times 2 times 4 to the k. Then here we'd have -1 times 5 to the k plus 4k, and -1 times 5 to the k plus 2 times 4 to the k. So a square matrix A is said to be diagonalizable if A is similar to a diagonal matrix, i.e. if A equals PDP inverse, where P is invertible and D is a diagonal matrix for this one. Theorem 5, the diagonalization theorem. An n by n matrix A is diagonalizable if and only if A has n linearly independent eigenvectors. In fact, A equals PDP inverse with D a diagonal matrix if and only if the columns of P are n linearly independent eigenvectors of A. In this case, the diagonal entries of D are eigenvalues of A that correspond respectively to the eigenvectors in P. So let's go ahead and look at example 3. Diagonalize the following matrix if possible. So what we're first going to do is I'm going to let A minus lambda I equal 2 minus lambda 1, 1, 0, 2 minus lambda 0, 0, 1, 1 minus lambda. So step 1 is find the eigenvalues. So we need our equation. So we'd have 2 minus lambda times 2 minus lambda times 1 minus lambda equals 0. Solve for that, and I'd have lambda equals 2, lambda equals 2, lambda equals 1. So my eigenvalues are 2 and 1. Step 2, find 3 linearly independent eigenvectors of A. And it's 3 because this is a 3 by 3 matrix. If this fails, you cannot diagonalize this matrix. Okay, so if this fails, you can stop there and say it's not diagonalizable. So that means we need to find the basis for lambda equals 2 and the basis for lambda equals 1. So I'm going to start with my basis for lambda equals 2. So that means I need to find a minus 2i. So I take a, which is and subtract 2i. And I end up getting 0, 1, 1, 0, 0, 0, and 0, 1, negative 1, I believe. Now we need to take and solve for a minus 2i times x equals 0. So I'm just going to write that in as a note. So we're going to be solving for a minus 2i. I think I said x by mistake. So a minus 2i times my vector x equals 0. So we need to use our augmented matrix here. And here, when I row reduce this, I end up getting, and what I can do is I can interchange row 1 and row 2, and then I can take my original row 2 and add it to row 1. So I'd have 1, 0, 1, 0, and then I'd have 0, 0, 0, 0, 0, 0, 0. So I would have x equals so x1 would be negative x3. This would be x2. This would be x3. So x would equal x2 times 0, 1, 0 plus x3 times negative 1, 0, 1. Okay, so that's our basis for lambda equals 2. So now we're going to find our basis for lambda equals 1. So again, we're going to do a minus I for this. And you end up getting, I believe, 1, 1, negative 1, 1, 0, 1, or excuse me, 0, 1, 0, and 0, 1, 0. So now we need to solve for a minus I times x equals 0. So I have my augmented matrix. And this reduces to, I can take row 3 and row 2, add them together, and row 1 plus row 3, add it together, and I end up getting 0, or 1, 0, 0, 0. I didn't do anything to row 1. I add row 3 to row 2, and I get 0, 1, 1, 0. And I add row 1 to row 3, and I get 0, 0, 0, 0. So for this one, I would have 0, negative x3, and then just x3. And this would give me x3 times 0, negative 1, 1. So that's my basis for lambda equals 1. So that's step 2. So you need to find your basis for this. And if I notice, I have 3 linearly independent vectors for this. So far so good because I have 3, and that's what you need. So then step 3 is construct P from the vectors in step 2. So P, if I called P, I'm going to call V1, V2, V3. And I'm just going to go and start with lambda equals 1. So I'd have 0, negative 1, 1, 0, 1, 0, negative 1, 0, 1. Here, order isn't important. In the next step, order is important in step 4. So I constructed P based on those vectors. Step 4, construct D from corresponding eigenvalues. So D, since the first vector I put in here corresponds to eigenvalue of 1, I would have 1, 0, 0, and then the other two eigenvalues of 2. So I'd have 0, 2, 0, and then 0, 0, 2. And remember, order is important, and these 3 are your eigenvalues. And then step 5 would be to verify that AP equals PD. So AP would be 2, 1, negative 1, 0, 2, 0, 0, 1, 1 times 0, negative 1, 1, 0, 1, 0, negative 1, 0, 1. When I multiply those, I end up getting 0, negative 1, 1, 0, 2, 0, negative 2, 0, 2. And then PD would be 0, negative 1, 1, 0, 1, 0, and negative 1, 0, 1 times 1, 0, 0, 0, 2, 0, 0, 0, 2. When I multiply those out, I end up getting 0, negative 1, 1, 0, 2, 0, negative 2, 0, 2. So AP does equal PD. And we're good. So we diagonalize the matrix if possible by finding the diagonalized matrix in step 4 from the eigenvalues. And we verified it by finding AP equals PD. So let's look at number 4. Diagonalize the following matrix if possible. So the first thing we need to do is we need to find the eigenvalues. And if you notice, this is a triangular matrix. So we can just go ahead and find our characteristic equation. We have 2 minus lambda times 2 minus lambda times 4 minus lambda equals 0. So I'd have lambda equals 2, lambda equals 2, lambda equals 4. So my eigenvalues are 2 and 4. So we're going to start with step 1, basis for lambda 2. So to do that, we take our matrix A and subtract 2i. And I end up getting 0, 0, 0, 4, 0, 0, 6, 2, 2. We need to solve for a minus 2i times x equals 0. So go ahead and get my augmented matrix. When I row reduce this, I can row reduce it to 0, 1, 0, 0 by taking row 1 plus negative 3 row 2 and taking a quarter of it. I can take negative row 3 and add it to row 2 to get 0, 0, 0, 0, and negative row 2, add it to row 3 to get zeros here. So I would end up having x would be 0, 1, or 0, x2, and x3. So I would have x2 times 1, 0, 0. And we're going to do the same thing for our basis of lambda equals 4. And so we would take a and subtract 4i. And we would get negative 2, 0, 0, 4, negative 2, 0, and 6, 2, 0. And then we need to solve this for a minus 2i times x equals 0, or a minus 4i. And when I do this, I would get, by taking row 1 plus 2 row 2, I get negative 2, 0, 10, 0. And row 2 would stay the same. And then again, I can go ahead and take half of row 1, negative half of row 1, and negative half of row 2. And I'd end up getting x equals 5x3, x3, and x3. So this would then be x3 times 5, 1, 1. So here, if you notice, I only get two linearly independent, there are not three linearly independent eigenvectors of A. So by theorem A, this is not, or theorem 5, this A is not diagonalizable. So we cannot diagonalize this. Let's look at example 4. Diagonalize the this is the same one. Let's look at example 5. Explain why A is diagonalizable. So let's go ahead and look with this as triangular. So I can find my eigenvalues. So I would have lambda equals 2, lambda equals 6, lambda equals 1. So this is a 3 by 3 matrix. And there's 3 eigenvalues. Therefore, A is diagonalizable. Theorem 6. An n by n matrix with n distinct eigenvalues is diagonalizable. So let's look at example 6. Diagonalize the following matrix if possible. So this is triangular. So our eigenvalues are lambda plus 2 times lambda plus 2 times lambda minus 2 times lambda minus 2 equals 0. So lambda equals 2 and lambda equals negative 2 are our two eigenvalues. So step 2, we would go through and find our basis for lambda equals 2. And when I do that, I would have a minus 2i, and a minus 2i would equal negative 4, 0, 24, 0, 0, negative 4, negative 12, 0, 0, 0, 0, 0, and 0, 0, 0, 0. Then I need to solve this for when it equals 0. So I need my augmented matrix. So we're solving for a minus 2i times x equals 0. And when you row reduce this, I took negative 1/4 of row 1 and negative 1/4 of row 2 to get those to be 1, 0, 0, 0, 0, and 0, 1, 0, 0, 0. And then I took 6 times row 1 minus 3 times row 2 plus row 3 to get zeros here. And our last row was already zeros. So x would be 0, 0, x3 and x4, which would then just be x3 is 0, 0, 1, 0, plus x4 times 0, 0, 0, 1. So I have two distinct vectors here. And then we have to also do this for lambda equals -2. So for lambda equals -2, we need to find a plus 2i, and that would be 0, 0, 24, 0, 0, 0, -12, 0, 0, 0, 4, 0, and 0, 0, 0, 4. So now I need to find a plus 2i times x equals 0. So my augmented matrix when I row reduce this, I can take 120. I'm going to go ahead and move row 3 to row 1 and take 1/24 of that. I'm going to move row 4 to row 2 and take 1/4 of that. And then interchange row 1 and row 3 and row 2 and row 4. And usually we don't deal with many fractions, but this one we do have fractions. And here I would have x equals so 1/2 x2 minus 1/6 x3, x2, x3, and 0. And then I would have x2 times 1/2 1, 0, 0 plus x3 times -1/6, 0, 1, 0. So we would find P, which would be V1, V2, V3, V4. So we'd have 4 vectors from our bases. And I'm going to go ahead, and if you want, you can always go back and label these. I'm going to go ahead and have this be V1, V2, V3, and V4. So I would have 1/2, 1, 0, 0, and then -1/6, 0, 1, 0, then 0, 0, 1, 0, and 0, 0, 0, 1. And then D would equal, they correspond to the eigenvalues. We'd have -2, 0, 0, 0, 0, -2, 0, 0, and then we'd have 0, 0, 2, 0, 0, 0, 0, 2. Then you just have to check, and when you do, check these, we would have AD equals PD, or AP, excuse me, equals PD. So theorem 7, let A be an n by matrix whose distinct eigenvalues are lambda 1 up to lambda p. For 1 is less than or equal to k, which is less than or equal to p, the dimension of the eigenspace for lambda k is less than or equal to the multiplicity of the eigenvalue lambda k. B, the matrix A is diagonalizable if and only if the sum of the dimensions of the distinct eigenspaces equals n. And this happens if and only if the dimension of the eigenspace for each lambda k equals the multiplicity of lambda k. If A is a diagonalizable and beta k is a basis for the eigenspace corresponding to lambda k, and k, then the total collection of vectors in the sets B1 to BP forms an eigenvector basis for Rn.